So why BICEP2 can measure BMO earlier than Planck? Because Planck is in space and the signal is supposed to be clearer than inside Planck, isn't it?
So BICEP2 had 500 detectors, and Planck only had a handful. Okay, so that's the thing with space mission, because planning takes a lot of time. So by the time you launch it, you're using old technology. So Planck was basically using BICEP1 technology. This actually looked a lot like a Planck focal plane. Right? And on the ground, we can rapidly upgrade when the new technology is ready. So this has more detectors, way more detectors than the Planck focal plane. So like I said, the total sensitivity of BICEP2 is comparable to Planck. We have more detectors, but each one is more noisy.
There's this other figure that you have all the other experiments plotted.
Yeah.
Where you've crushed them all, right?
Yeah, so we were debating whether to publish this.
This one.
Yes, whether we should publish this,
Where all the quiet experiments,
yes.
Right? How do you explain those?
Well,
what's wrong with them?
nothing. These are great experiments.
Oh, come on.
It's just sensitivity. You need to get to the sensitivity.
Is it the detectors or the number of detectors?
Yeah, both.
Okay.
So the name of the game in here is really the sensitivity. So we do have to deal with systematics, which I didn't get into. But if you don't have the sensitivity, you don't have systematics to deal with. That's not a good problem. So it's really the sensitivity. So I can give you some numbers. So BICEP1, the sensitivity is 35 microkelvin per second. BICEP2 about 16 or 15, and the sensitivity R is the square of that number. Quiet Q band and W band is about 90. So again, the square of that number becomes much bigger. These are really earlier generation experiments. It's hard. It's not easy, but
so the quiet is not at the same frequency.
So this one is at 44 gigahertz. This one is at 90 gigahertz. So these are these points. Right.
Yeah. Great talk. I have a question on this slide. It shows that lensing can produce BMO.
Yes.
Lensing is a stretching of space, but not so much in time, right? It's not gravitational
it's
wave.
actually simpler than that. So it happens much later.
Well, my point is this, okay? That if lensing can produce BMO, admittedly at different angular scales, how are we sure that what you're seeing is really from gravitational waves at the smaller scales? Maybe there's some, structure that we just don't know about at such angular scales, which are actually not gravitational waves, but are more like lensing.
So this signal is produced by gravitational lensing of primordial E mode, which is very well understood by intervening large-scale structure, which in this regime at Z of 3 or 4, okay, is very linear. Okay. So when I said the null hypothesis was ruled out at, in fact it's 7 sigma. It includes the fluctuation from gravitational lensing induced beam. Okay. So unless we're talking about completely non-Gaussian, something just evilly blocking our view in front of us and we didn't know, then it's statistically extremely unlikely that lensing can create it. It's mathematically possible, yes, indeed. But, beyond reasonable doubt, we don't think it's lensing at all. Because this is very well understood physics. It's, interaction between two linear fields, two Gaussian distributed linear fields.
produce a large scale structure, you really need something close by if there's a fake. And so in this regard, did you worry about the dust? And although you say the dust cannot have any effect, but suppose you have to disentangle this issue, and probably you have to increase the frequency coverage.
Yes, indeed. So we know this is not systematics. We don't think this can be dust foreground, but again, it's a mathematical possibility that we can't rule out yet. We really don't think so because there's no foreground modeling we can create this pattern, which is now much bigger but with a very different shape. Yeah, so these are attempts of foreground modeling. As you know, from our galaxy, the foreground tend to have a folding spectrum, not something that just looks like inflation. But we're going to follow up very quickly with, we put in two 95 gigahertz receiver this year. So we took two 150 gigahertz focal planes out and put in two 100 gigahertz focal planes this year. Hopefully we can quickly confirm the color of that signal. And just in 6 months or 9 months, we're gonna have way more detectors at 100 gigahertz with BICEP2. So yeah, we'll rapidly follow up.
Yes, I believe it's the third to the last page. Well, sorry, maybe further. One more. No, I mean, back more. Yes, here. The next page. No, I mean, sorry. I apologize. I mean, no, not that far back. The one that I stopped you, and the page after that. The one, yes, here. So the dash curve. My question is there any of these curves the fitting of your data?
Yeah, so I believe this is R.2, which is the best fit from this likelihood function, 0.20. But it's not like we can change the shape of this at all. So the shape is completely fixed. We can only change the amplitude.
I guess my major concern is about the part of the data that's embedding into the lensing part.
Yeah, so
Yeah.
this is only 2 signals.
Okay, and that's the best fit to your that curve,
Yeah,
the long dash.
including these points or not, we get pretty much the same fit because we're completely dominated by constraining power here.
Okay.
Here it's dominated by lensing anyway, and yeah, it's a very good fit.
It's a fit with only 2 components, right? That's why you cannot fit any better. It's just this part.
So this part dies out rapidly. So you can't
Gotcha.
you
All
can't
right.
increase this to solve
Yes,
any
thank
of
you.
this. I should also mention, if you look at the KEK, the BICEP2 cross KEK, these points scatter low again. So we really believe this is just random scattering.
Okay. In your conclusion, you mentioned that you prove the existence of graviton, gravity is quantized. How? The question is that how do you prove that?
So this is the simplest explanation. So we don't directly detect graviton as a quantized particle, but a standard prediction, as I was walking you through in the first few theoretical slides, right? This gravitational wave background was coming from amplification of the vacuum fluctuation of gravity. Okay, so that's the standard mechanism for generating such a thing. And it works out brilliantly for scalar perturbation. Okay, so I really think this is many theorists agree that this is really the default mechanism for generating a gravitational wave background.
There's a question. Oh, there's another one.
Or, I guess it's just a comment with the tension with the Planck data. The Planck data was actually measured with, I thought, WMAP E-mode polarization and the power spectrum. So I guess the idea is that if you have B-mode, it can scatter also into E-mode, and therefore you should be able to measure it. So there might be some additional physics or cosmology that's part of that tension, and Planck still hasn't released their polarization data yet.
Exactly. So this WP is WMAP polarization data, primarily in low L, to constrain the optical depth of reionization. And both Planck and WMAP use that data. And that does create some degeneracy, or redundancy, if you will, meaning the Planck constraint and WMAP constraints aren't completely independent.
But my question is that is any other physical process that could produce this kind of large scale BMO?
I don't know, I think it's a question for the theorists. So I'm an experimentalist. It's hard for me to claim that we've detected primordial gravitational wave, but I'm going to ask what else? Tell me, let me know. It seems to be the simplest explanation.
So since string theory has been queued quite a few times in this talk, I feel compelled to make a quick comment. So it's basically in regard, I think the second or third last slides where you have a summary of all the theoretical models, right? So basically, it's true that what Chao-Lin was saying, that most of string motivated model has been rolled out, and one of the reasons is closely tied to the statement afterwards that most of string theory model either they generate, or they have many fields, and that will produce a non-Gaussianity, which has been also disfavored by the experiment. But also that a lot of string motivated model has only give a small field range. So basically, like for those of you who have taken like quantum field theory 101, that basically if the scale is super transplanckian, and if you in small field, that means the field actually carries a dimension of mass, and that's very small compared with the Planck data. Well, so Planck mass. And the point is that now if you want to have a large or super Planckian range, then you should know that there's actually UV correction into your infotone potential. And it's crucial to, like when Chao-Lin was saying about the inflation introduction, it's crucial to have very flat infotone potential to generate enough number of E-folds. But in order to do that, you have to take care of all this UV correction from this super Planckian displacement. So I think, as Chao-Lin was saying, it's actually quite exciting time for basically a new theoretical model building, and whether from string theory or from other possible theory of quantum gravity. So that's just a comment I want to make.
As you mentioned, you have already looked at the specific guides at the South Pole, but is that going to affect tensor to scalar ratio that when you measure in larger sky? Because you seem to focus on the area that do not have very strong foreground, right?
So if you look at this dust map, at the South Pole we're primarily limited not by available good sky, but rather this declination limit from the fact that we're at the South Pole. So there's plenty of good sky to look at once you're in mid-latitude site. You have to go north, Greenland or something to see this, but you can see a very healthy patch just by going to Chile.
So, will this T-Rex be in Atacama Desert? Or?
Yeah, we just started thinking about it. But it seems to be a very well motivated experiment.
I have two questions. The first one is, it seems that the experimental result from BICEP2 deviates apparently in a small angular scale from theoretical prediction. What do you think about it? And the second question is, there is some so-called barioacoustic oscillation also caused in the same region as the CFB. Is it possible for us to detect the result of gravitational wave from it? Thank you.
So yeah, so like I said, the apparent excess at L of 200 is really not very significant. Again, it's a 2 sigma level, and with Keck, it's gone. So it's really hard to comment on 2 sigma things, other than just to call it a scatter, a random scatter, without a significant deviation. If you look at the best fit of lensing, which I had in my backup slide. So this is a fit of R, a two-dimensional fit of R versus the lensing scale factor, 1 being the standard model amnesty prediction. And we're really consistent with that. I wouldn't say we have any reason to believe we detected an excess. We didn't detect any excess at all. When everything is done appropriately. So the second question is
BAO.
Oh, BAO. Yeah, I think there are a few papers on using, I don't think those are called BAO, but using large-scale structures to search for tensor model fluctuation. Yeah, seems pretty hard to me, but didn't stop the theorists writing papers. But it's possible, because this thing was like science fiction just 10 years ago, but now here we are. So who knows? Maybe it's possible.
How serious is your power leakage between the E and the B mode? The B. Maybe you have the power leakage from the E mode to B mode, right?
Yes. Oh yeah. So like I said, it was done now in a matrix operation, in a very simple matrix operation. That was this step, right? The total observed polarization to the purified B mode only map was done with a matrix operation that involves a giant eigenvalue system. And you can just evaluate how well that procedure works by feeding simulated E mode only maps, right? And you look at the output B, and we did that. And the level of R we've seen from that is around 10 to the minus 4. Okay, that's completely negligible compared to the level of R we see. This seems small, but it's not leakage. It's huge compared to leakage by orders of magnitude. we're working on a paper to write up that procedure. So the result paper is really highly condensed. So there will be a few method paper, analysis paper coming out in the next few months. Other questions?
You know, throughout history, we always say we live in interesting times, the best of times, right? But for astronomy, it's really amazing that now we have the technology sensitivity to detect an effect such as this from the earliest moment, right? So it's really, truly amazing. So for the young physicists in here who are preparing, you know, this is your future, right? So there are many things that are possible. So you guys should be paying attention. I hope you're inspired. And let's thank Chao-Lin to come and give us this wonderful talk. And he promises to give this thing again tomorrow in Chinese. Right?
It's a public level without equation.
Do we have coffee afterwards?
你们有带电脑来吗？